Stop recording.
Yo!
Stop recording.
I will start. You should It's fine.
Miles.
It's cool.
Miles. Click stop recording.
Okay.
Now you're good. Now go to your presentation.
Funny. Super Sam Chen. Okay. Alright, well, I'm gonna start now. You don't need to applaud me. Not yet. This is my presentation about control theory for FRC. I'm the president of software engineering for Team 694. And control theory, having a presentation like this hopefully provide a good grasp is super important for software because control theory will kind of unlock consistency in your mechanisms, or the mechanisms that the engineering department builds, and it provides a solid foundation that you can build more advanced software on top of. Because once you have reliable control theory, you don't have to worry about it ever again. Your mechanisms should do what you tell them. So let's get started. What is control theory? So there's like lots of definitions in textbooks, and like the next slide is kind of a textbook definition. But just to start off, my understanding of control theory kind of goes like this. Motors only speak the languages of voltages and percentages, right? You can't just tell a motor to go to a position, and you can't really tell it to just spin at a meters per second or to spin at an RPM. So the problem control theory is trying to understand is how do you calculate a voltage or a percentage to actually get a motor to do something that you care about, and that would be like running at that like meters per second that you want it to, or going to that like height or like angle you're asking of it, right? So this is like hopefully illuminating as to what problem we're trying to solve. But then this is like a simplified textbook definition. It's like using mathematical formulas to drive a system to its desired states. So there's clearly like a couple terms in here, and they kind of like spoil the surprise that there's a lot of math involved. But let's just get into defining some of these terms, and then maybe we can make this useful. So the system is simply just a thing you're trying to control. So I don't know why there's 3 elevators, but I just realized that. So this would be just a subsystem of your robot. The drivetrain, shooter, climber, elevator, right, are all examples of subsystems that will likely require control theory, or that you can like benefit from applying control theory to. Some subsystems won't require them if they're simple. You don't want to overcomplicate them in that case. Like if you just need a subsystem to run at 100% forwards and backwards to like intake balls or something, then you don't want to overcomplicate that. So your system is what you're trying to control. So a system state, every system has a state, and it's just the properties that you are trying to control from it, right? Or that will be like beneficial for helping you control it. So this would be the velocity of a shooter and the height of an elevator, right? You don't really care about the speed of an elevator. You just care that it gets to the height that you want it to, and you don't care about like what rotation or what angle a shooter wheel is at, because it doesn't matter. You want it to just be spinning and constantly changing position. So then the way you control these systems is with an input. So input will change the state of a system, and there are equations that will let you know how that's done. That's like outside the scope of this presentation, but the most common one is most common input is voltage. So for example, voltage will just change the speed of a shooter, and will spin the motor of an elevator that will cause the like entire thing to slide up. But we also have to define measurements, which are the states of a system as understood by sensors, right? Because in the actual state of the robot is really hard to get a real reading of. So measurements are really just estimates, right? Like sensors are not perfect and they have noise and randomness. In FRC though, they're usually good enough. It's another aspect of control theory, like fixing your measurements to get a better idea of the state, but again, like also outside the scope for this presentation and probably FRC a little bit. So you can also think of the state as the truth, but getting like, this would be like if at every instant you pulled out like 2 rulers and like measured where your robot was on the field, that would be like the truth state of your robot, but of course that's hard to get, and you can only understand like where your drivetrain is from the sensors. Measurements are also called outputs. That is from like a more advanced equation, and output is like a confusing word because it's the complement of input, so I will not call it output. It's just a measurement. So yeah, the references is kind of like where the human comes into control theory, like why it's useful. You're picking a reference is just the goal state of the system. So you pick any state that you want your system to be at. That's the reference. You also call it the set point, right? So you just pick any state you want to be at. For a shooter, this is the desired RPM, and for an elevator, this would be like the height, right? And in FRC, references can come from anywhere. Like that's what I was saying before. Like the beauty of control theory, the references come from anywhere, as long as you supply them to like a good control theory implementation, whatever, it'll work. So that step is called planning, like how you're calculating your references. So this could be from the driver or operator, right? So a gamepad, if you want your, if like the velocity of your drivetrain to follow your joysticks, that's an example. An autonomous path, so calculating velocities, again, this could be for a drivetrain, along a curve, so the drivetrain then follows that curve, or a computer vision routine, right, calculating how far you need to go, and then through some mechanism feeding that to a control loop. All of these are valid references. This step is called planning, though. This is what I mean, like you can put any advanced software on top of control theory. Error is another useful term to define because if the goal is like getting a system to desired state, you have to think about what it's currently doing, and that's the measurement. So just the difference between the reference and the measurement is the error. So if we had a shooter at 1700 RPM, but we really wanted it to be at 3500 RPM, like we're shooting from like a launch pad for the 2022 game, we're just shooting from very far away. We want the shooter to spin really fast, right? And then the error will be 1800. So yeah, this slide puts all of that together because it's defining what a control algorithm is. Hopefully, now that we have all these terms defined, this sort of like rigorous definition will be more helpful. It's going to use the reference and the measurement and then calculate a voltage to feed to the system. Once this voltage is fed into the system, it will affect the future measurements of the system, and then a good control algorithm, the the voltage that you're feeding it will therefore drive the measurement to the reference, minimize error because like the error is the difference between them. If they're getting closer, you're going to zero, and just like error just sounds like something you want to minimize, right? You don't want any error. So the kind of similar example to the last slide, if your shooter is reading 1700 from its sensors, but you want it to be at 3000, a control algorithm will use those few values and calculate a voltage. It will feed that to the motor that's spinning the shooter, and ideally, with a good algorithm, the RPM of the shooter, right, that 1700, will get closer and closer to 3000. So, yeah. I mean, I guess I have a lot of time. So does anyone have any questions? Anything that they want me to clarify really quickly before I move on? Yeah.
So, okay, so what we went over is that for a system, could you redefine that? I'm not sure if that's the.
Oh yeah. So a system, it's kind of like a pretty abstract term. It's just the thing you're trying to control. So a group of motors and sensors you can consider a system. But yeah, it's just yeah. Does that make sense?
Yeah.
Okay. Yeah. It's not a very satisfying definition, but if it has motors, you can control it. Is there any other thing I can clarify?
The input. Well, there's another name for it.
Oh yeah. The input is something that you can feed to the motors of the system, and that's usually just the voltage.
Yeah, but there's like another name you put here.
I think that was measurements. Measurements are also called outputs. I was just saying that I don't like that name because it's complementing inputs and it's like confusing. So we just have system, state, measurement, input, and references.
Could you go over states?
Yeah, state is just the property of the system that you're trying to control. So if you have a shooter, right, you want it to spin at a speed. So you're controlling the velocity. but you're not controlling the position of the shooter because that's not relevant to you. It's not relevant what like angle your shooter's or like if you have the wheel, you don't care like what angle it is. You just care that it's spinning at the right speed. So then for the elevator though, you want to control position because your goal, like as a human or like as a programmer, your goal in designing this control like theory thing is getting it to go to a position. So your state is a position because that's what you want the elevator to go to. Does that make sense?
Yeah.
Okay. Yeah.
What would be the math behind getting an RPM based off like a motor input?
Getting the RPM from a motor input. Wait, RPM from the RPM from the voltage. I mean, you can use a sensor for that, but I'll go over some of the math, like in a bit. That's like in like 6 other slides. Yeah.
I'm sorry, did this class just start?
No.
Oh.
Okay, so control theory for FRC. Luckily for FRC, this is like a pretty general topic. I've been getting pretty general definitions, but for FRC, you can apply this knowledge to only 2 use cases, and like that'll cover all your bases for every mechanism that you can have on a robot. So the first one's position control. I mean, I kind of mentioned this just through the examples I was giving, but it's just like controlling the position, state, position. I could be meters. Your reference will then also be meters. Your input to the motor is usually voltage, and that's what your control algorithm will calculate. And then common cases of this, I mean, I gave the elevator already. State's the height. Turrets also need position control, and their state is an angle, which is still a position. There's, I think, one caveat about that, though. When you have a system that can move continuously in circles, when you have a system that can move continuously in circles, and this would be a swerve module or a drivetrain like spinning around itself, and this could be for like alignment or something where it's spinning along that circle. A turret wouldn't actually apply here because if it spins in circles continuously, it'll rip itself out. So you need to do you gotta hard code something. But in those cases, you can use angle math, and that'll prevent you from taking like a redundant route around a circle. Because if you have 179 degrees as your measurement and 179 degrees as your set point, if you subtract the two and find error, you would end up with like 358 degrees, which is the red line. Whereas if you used angle math, which will just consider the fact that it's on a circle, you just go 2 degrees the other way. And it's the same thing because it's on a circle. So yeah, position control with angles is the same thing. It just uses slightly different math to calculate error, and you get better results. So for swerve teams, like this is what you'd want to do. And if you've like looked up swerve, you've probably come across this already. But this is kind of, I guess, what it means. And it's a little bit more general. You can apply it to a drivetrain as well, or like alignment of a drivetrain. So that would be like turning left or right. Yeah. So then the other use case is velocity control, right? The state velocity, set point velocity, and the output. That should say input, actually. Yeah, that's why it's confusing. But basically, what this is calculating and feeding to the motor is a voltage. And then, yeah, this can be in any units you want. Meters per second if it's like a wheel traveling on the floor, or an RPM if it's like a shooter wheel. And the common cases, I mean, I've probably said it a bunch of times. Shooters need velocity control algorithms. RPM was a convenient unit for us. I can imagine rotations per second also being useful. Drivetrains need velocity control for the speeds of the wheels. They actually, for a tank drive specifically, you would need like a left control algorithm for the left side and a control algorithm for the right side. They can use the same like constants and whatever, and I'll get into that a little later. But yeah, you'd be using velocity on both sides of a drivetrain. Oh yeah, I had a note because like drivetrains are really complex. You want them to do a lot of things, so you want them to go at speeds, but you also want them to like go to certain positions, look at certain things. So the position, you can use a positional control loop that calculates a velocity. That could be, for example, how fast you want the drivetrain to turn. And this could be turning towards a goal, the hub in this pass game, and it can feed that velocity to the velocity control loops that are controlling the wheels. So that would be an example of planning. it's just a really common case of it. So I thought I'd bring it up. So yeah, we can get into our first algorithm here, feed forward. So, or actually, did anyone have any questions about this? Yes.
I don't have a question.
Yeah, sure.
Just like, I don't have enough time to copy down the slides, so just slow down a little bit.
Oh, okay, yeah. Thank you for saying that. Is there anything you need to copy from here? Also, the slides are posted. If unless you're taking your own notes, that like helps you understand it. The slides are posted.
This is also being recorded, by the way.
Yeah, this is on camera. Me telling you this right now, you can listen to this again.
Wait, what is going to be posted?
We'll send it out soon. After 4:30.
Yeah, like an email, because like in the form you give your email, and also on the website, StuyPulse.com or whatever. But yeah,
The recording will be on the YouTube.
it'll reach you. So yeah, do you need this slide still?
No.
Okay, cool. So feed forward, first algorithm. The goal of feed forward is to use a mathematical model of a system to calculate a voltage given a reference, right? So this is a control algorithm. Even though it doesn't rely on the measurement from a sensor, it's still a control algorithm. Or at least the way we think of it, it is. The references are basically always velocity and acceleration. So just an example of this with like real numbers and real mechanisms. If you calculated 6 volts for a shooter, given the fact that you want the shooter to go at 3,000 RPM, and you can feed that 6 volts to the shooter. And we'll talk about how that's calculated like the next slide. But then just the mathematical model here, like in quotes, it's just an equation that when you plug in velocity, the desired velocity and acceleration, it'll give you back the voltage, and that voltage goes to the motor. And every like mechanism on your robot will have a slightly different equation, or maybe not a different equation, but like different numbers, coefficients in that equation, because each system on your robot behaves differently, like different physics. So then how do you find these models? Because like if you don't have a model, then this method is not useful. So you can find theoretical equations through like Newtonian mechanics, physics class. So stuff like F equals ma will help you here. And you can use the fact that motors produce a force when given a voltage. So on the left, so when you have F, you can replace that with like an equation for a motor. But that's kind of hard, and probably not as helpful because these equations are only theoretical. And they just might not reflect the system as accurately as collecting data can. So yeah, if you want to empirically find a model, go down the data collection route. What you would be doing is collecting data on the state, right? So recording the velocity and acceleration when you feed your system various voltages. So then a best fit relationship will be made between the variables, which is like a 3D line. But then you just take the inverse of that so that you can plug in velocity, acceleration, and get the voltage because you're originally plugging in voltage and recording the velocity, acceleration. But this process in general is called system identification. And this happens, or like for FRC, the main tool that you want to be using for this is WPI-Lib sysid, right? If you have WPI-Lib VS Code, you already have sysid. It would be hard to download one without the other. So what sysid will tell you in the end is these 3 constants, Ks, Kv, Ka, that are a part of a larger equation, right? So they're just like numbers, coefficients in that equation. And those are allowing you to calculate voltage given the reference velocity acceleration. So what the full equation looks like is this. A lot of text, but we already covered like what it's doing. So Ks okay, yeah, so just on the left, the big V is voltage. The A all the way on the right is the target acceleration. The V's, right, SGNV and V are the target velocity. And then SGNV is like the sine function. So when the target velocity is forwards, so positive, it'll return 1. When it's backwards, so negative, it'll return -1. And when it's 0, it's 0. Why do you SGN the velocity? That is because Ks, or then Ks, Kv, Ka are your physical constants that sysid tells you, and they have physical meaning, right? They kind of have like meaning for the real world. So let's start with Ks, because I'm about to get into that anyway. It's a constant that represents the voltage required to overcome static friction. So if you have like a gearbox, or controlling an elevator or like a drivetrain, it's not going to be perfect, and there's like going to be some like friction internally, or like maybe not even just related to the gearbox. There can be other inefficiencies, but there's just going to be some voltage required to overcome static friction, right? To overcome that like resistive force, and that is what's stored in Ks, right? The reason you multiply it by the sign of the direction you want to go in is because you want to, if you, it's resisting your motion. So if you're going backwards, you want to apply that voltage backwards, and if you're going forwards, you want to counteract friction going forwards. So yeah, and then like if you're not moving, where it's 0, you don't want to apply any voltage. So then kV is just like representing the voltage required to coast at a velocity. So it's just like a simple way I think of it is that the units of kV are like voltage over the unit of velocity, right? So when I multiply the target velocity by units, or velocity times voltage over velocity, I'd get back voltage. And then Ka is kind of the same scenario. It's the amount of voltage required to induce an acceleration in your motor. And this is like units of voltage over like acceleration, so like distance per second squared. So when you multiply by acceleration, it cancels out, get voltage. You have 3 voltages, which means you can add them up and get the whole thing. So this feed-forward equation, that final voltage can be sent to your motor, and it'll achieve the V and the A that you've asked for. There's another feed-forward equation, which, I mean, if you look at it, it's the same thing except for one term, kg. So for a system that's affected by gravity, it's useful to know the amount of voltage that will cancel out the force of gravity. So if you had nothing else in this equation but kg, what this will mean is that like you're always feeding kg to the motor that's controlling the elevator, and the elevator will never sink, right? It'll hold its position, which is really, really useful when you add on all the other terms, because all these other terms are describing the motion of the elevator. So if you can cancel out that falling, you can have like accurate motion on your elevator, as kind of as if there was no gravity. So for like a operator that's controlling this elevator with the joystick, this is super useful. So when he lets go, like the elevator won't start falling. Oh yeah, I have a note. For an arm, you also can account for gravity, except it's not a, or kg is a constant, but the term that's canceling out gravity is not, because you're multiplying it by the sine of the angle that the arm is at. Yeah. So a note on models, like this is pretty simple. Once you collect data, like this whole equation, right, it's just like multiplication and additions. It is simple, but it is not like 100% covering all your bases, because you can't make a feed-forward model between like voltage and position, because there's no like voltage that will induce a position. It'll only change your position. So this can only be applied to the velocity use case. So feed forward can only be applied to velocity, or feed forward alone can only be applied to a velocity control scenario. Right? So yeah, there's like no voltage at the bottom. Another way to think about it is there's no voltage that will make the mechanism teleport to position. But we'll see how you can still use it later. So yeah. If we wanted to put it all together in this example, feed forward, I was saying before, it is perfectly valid for velocity control if feed forward's on its own. So you can use like a velocity feed forward algorithm for a velocity system like a shooter. So if I've collected data on my shooter where Ks is 0.17 and like Kv is 0.002, you have this function. This function is voltage is the output. Your input is RPM. You have 0.17 times the sine plus 0.002 times the RPM. There's no acceleration here, because for our shooter, or just for a shooter, we generally just like set the target once and didn't change it, which means that our target speed is not changing, and therefore there's no acceleration. Because acceleration is your change in velocity over a small change in time. If you plugged in 3,000 RPM, you'd get 6.17 volts, which seems about right. That's not like 100 volts, which would be ridiculous, or like a really small number. This seems about what you would expect. And we can set the shooter motor to that, and it'll all work out in the end. I believe I have a demo. We can tune it. We won't use sysid, but we can kind of see what happens when you're trying to control, like, we have a shooter, and we can try and control it with like different KV, KS, and KA values, and we can see what happens when it's off, or like when the numbers you have aren't great. We can find good numbers and see how powerful it is. So hopefully this isn't like going to grind the computer to a halt. So yeah, I'll give it a minute to try and start the simulated robot code we have here.
That's my list.
This is yours.
No, that's
No drinking in the auditorium, by the way. Okay, so here's my graph. Let me explain what's going on here. So on this graph, oh man, I feel like those lines are not good to look at. But hopefully this is somewhat visible, right? So this is a graph of like the x-axis is time and the y-axis is the RPM of a simulated shooter. The blue line on the y-axis is the target RPM. So there's going to be an orange line that shows up, and like we're just going to want to see how it reacts. So there's like, this is just feed forward. So there's an equation. I can actually show you. So down here, I have KS, KV, and KA. And when we start plugging in values, we can see what happens. The like 3000 will be plugged into this equation. That'll be fed to the simulated motor, and we'll see the orange line approach the blue line. So if I give a really like ridiculously large number, just like 1,000 or 100 or something, right? We see that it goes to like a number that's not physically possible on a real shooter. Or actually, I think it did get capped out. I think this simulation like caps out, or like the numbers I gave to the simulation caps out at about 6,000 RPM. What if I give it 1,000? Okay, yeah. I think it did go. I don't know what happened, to be honest. But yeah, when I put it back down to 0, it like comes back down to earth. So if I like, obviously, what if just 1 worked? That also, we can see the voltage that's being fed to the simulation. It's 3,000, which certainly makes a lot of sense because it's the formula acting right now is 3,000, the target RPM, times kV, which is 1.0. So if we want to get it down into like the range of like a different order of magnitude, so like in the tens at most for 3,000, we want to have a pretty small number. So like if I do 1,000th. Oh wait. Okay, yeah. If I do 1,000th, it comes back down, but it's like at the wrong RPM. It is getting like 3 volts though, which is pretty good. And this will kind of hint at like the tuning, the step I'm going to take next, right? If we want to like, we want to approximately double the RPM because it's at 1,400 right now, and we want to be at 3,000. So we can simply just like double this number, right? And now we're basically almost there. We can say what's happening is attributed to KS because we haven't like if there's static friction, right? Occurring here, then using KV alone will not be perfectly accurate. So if I add on, so it's 3,000. I need to add on like let's say about 0.2 that I want to add on. So Ks is going to get multiplied by the sine of the target RPM. So that's 3000, right? So that'd be just 1. So whatever I type in is just going to get tacked on. So I tack on 0.2. Right now we're perfect. Right. So the simulation I created had the numbers like Ks 0.2, Kv 0.02, and we're kind of ignoring acceleration because we're not really constantly changing the set point. So yeah, that is what happens, and you can see that it works. Do like 1500, it responds pretty nicely. 1000, like 3600, 6000 even. Yeah, it's just responding to all these inputs. It tracks them pretty well. The feed forward did most of the work on our shooter this year for the competition season. So yeah, that is for now. That's like the knowledge on feed forward. Are there anything that anyone wants me to clarify on this for right now? Yes.
Yeah, I have like 2 questions.
Yeah.
So, what you're doing right now, you set, like the different values you're changing, those you've already set for the, like, simulated motor, you're just trying to find that, right?
Yeah, because in real life, we wouldn't know those numbers, right? Those are just numbers describing like the real life physical behavior of the shooter. So we would run data collection to find them. Here, I was just showing you like what would happen if we were manually tuning them.
And then also for this, like kind of like feed forward, if there was like like a different kind of error, like there's like more friction, that would cause it to like stop working, right?
Yeah, if there was, I suppose, a non-constant friction term, you would need to account for that. But we'll learn about an algorithm that will react to like. I'm just gonna put PID on the board in a second. But yeah, if we had unexpected errors, we could use a different type of algorithm that's reactive to error instead of only reactive to set point. Yeah, more questions, Sam.
How do you use this ID to find the specific K values?
So you'll, let me see if I can pull up sysid. That's a good question. It's a practical question. So sysid, what it's going to do to actually run the data collection code on your robot, you're going to put in motor controllers, ports, and coders in this section right here. If you can see it in like the top corner, it's called generator because it's generating a robot project that's going to deploy to your robot. And then the logger over here, this will like, oh yeah, this is just like connecting to the network table of your robot once you've deployed this project you generate. And then these tests over here, quasi-static forward, backward, and dynamic forward and backward are different tests that apply voltages in different ways in order to like extract that kV value and like get good acceleration data. Because these dynamic tests, it's a step input, so it'll instantly give it whatever voltage you specify here, and it'll see how it responds to that, see how it accelerates, and then this over here, quasi-static, it'll give it a ramp rate, which is in volts per second. So like every time input, it's going to give it slightly more voltage. So there's like a constant acceleration here, but so you can collect velocity from that, the kV number. So once you run those tests, like let's say it's on a drivetrain, it'll literally just drive back and forth, right? You'll save the data into like a JSON, and then this analyzer section over here, you'll load it up. There'll be feed forward analysis and feedback analysis. I'll cover feedback in a second, but in the feed forward analysis section, there will literally just be 3 rows, and each row would like be KV, KS, KA, right? Does that make sense? Okay, so yeah, you're just gonna read them from a data file that sysid collects. Yeah.
I mean, we're talking about flywheels specifically.
Yeah.
Will feed forward be enough to control them, or is there really any difference between using solely feed forward or between that and implementing feed forward with PID?
So yeah, I'll cover more about feed forward and PID in a second. But if you like know already about it already, this feedback analysis section will give you PID gains to combine with feed forward. So it's like pretty cheap to get the PID constants to like add on top of feed forward, and then you just use like a library to implement the algorithms for you, and you just use the numbers that are in here. Feed forward generally good enough. If you notice issues where like the speed is not able to get back up, and so like if for this game shooting 2 balls pretty like rapidly, cycles really quick. So if you notice that second ball is not following the same trajectory, that's when you might need a PID because there's unexpected error from the first ball leaving the shooter, right? Like it just couldn't spin as fast. So technically those constants changed. That was unaccounted for though. So then when the second ball goes out, spinning at a speed that you might not expect, if that is a noticeable issue, then that's when you might want to put in the extra effort to put some extra measure on it. And that extra measure I will cover right now. So yeah, feed-forward algorithms are really powerful, right? They don't rely on sensor measurements at all, which is really nice, except when you're collecting data. And you can like basically instantaneously calculate a voltage that will make your system go to like the desired velocity, right? That's something that happens instantaneously. You just plug it into the formula and you get out this voltage. So that's another benefit. So on the other hand, there's like a feedback algorithm, right? I suppose the complement to feed forward. And feed forward, while powerful, is only using set points. So it does not account for disturbances that occur while running, right? So like it's only taking the set point and calculating a voltage from that. So it doesn't actually know what it's currently doing. It doesn't have a measurement. Whereas feedback algorithms take in a set point and a measurement and can calculate the difference between them, the error, to then calculate a voltage that you can use for the system, right? So then as a result of like that fact, feedback algorithms are reactive to error, right? If there's error in your system, right, a feedback algorithm can account for that. And I already mentioned the 3 letters, but PID is the ubiquitous feedback algorithm used throughout FRC and probably a lot of other applications as well. It's pretty historic. So yeah, like the last slide, takes in a set point, takes in a measurement, calculates the error, and then uses that error to calculate a voltage for the system. These can be position or velocity, so it'll work for either one, whereas feed forward's only velocity. But we'll see more about like the caveats of that. So how does it work? This looks like a lot. There's like technically calculus in here, but that's just like notation to put it in one formula. But it's kind of a similar ordeal. You're plugging in error and you're getting out a voltage, right? So this Kp, or V is the voltage, E is the error through all these different like symbols. So this first term all the way on the left, the proportional term, Kp times A. Kp is a constant, right? It's just another number that you're going to need to find. And I was saying a little bit before how sysid can tell you those. So it's just a constant, and you're multiplying it by the error. Ki is that Ki times the integral of E of error with respect to time. That's like what that calculus notation, that's how you would say it. But that whole term, Ki is the constant, and then the integral you could think of just as the accumulation of error over time. So it's like built up error that you want to fix, right? That's where this term would come in. And then Kd is, again, the dE over dt is the rate of change of error, right? How much it changes in a small period of time. And you're multiplying it by the constant Kd. And that whole thing's a derivative term. So that's where you get PID from. The first one's called proportional because you're just multiplying them together. So yeah, what does it mean though? Yeah, I'm going to break down what all the terms mean, but PID accounts for all of them simply by just adding the 3 terms together. So yeah, first one, proportional term. What is this one doing? The P term really does a lot of the work in PID because when the system is not at its goal, right, the error is going to be probably the most significant thing there. Right, the error is going to be really big, which means that the V that you're feeding to your motor will also like therefore be really big. But then as you get closer and closer to your target, this Kp times E term contributes less and less, right? Because E will be smaller, or the error will be smaller, so therefore this whole term is smaller. The integral term can handle past errors that weren't accounted for, and then use them to contribute to the output voltage. So in code, or like in an implementation in code, integral of E, right, the like sine E dt, is just error times dt added to like a total error, added to the accumulation, and then you multiply that accumulated number by ki, right? So yeah, when there's error that wasn't accounted for in the past, that'll be accumulated and then put into the voltage output for a PID algorithm. This, if this is confusing, you don't have to worry about it because I'm going to tell you that you don't want to use it in a second anyway. But then the derivative term, this is responding to the speed at which the measurement is approaching the target, right? So kind of what this means is like, if your measurement is approaching the target, that means you're going to have some sort of change in error. That's what that term dE over dt is. It's a change in error. So as your measurement approaches the target, you'll have negative dt because your error is decreasing. So your change in error is negative. This means that as you're like approaching your target, this term kd times dE will slow you down. So you can also think of this like if you're coming in hot on a target, if you have like a good KD value, it'll slow you down before you just drive right past it. And then if the error is in, oh yeah, do you have a question?
So of course we're finding KD, KI,
Yeah.
manually, but in regards to E, it's being treated as some version of a continuous function. There's something that you just find a lot of data in the text, define a function that connects the dots.
Yeah, that's actually a really good point. I was saying before how this like this function, this calculus notation, which assumes that there's a continuous function for error over time, is not actually what's being implemented. It's just to put it in this formula. So what's actually being implemented is you have some accumulated error, then like every time you use this formula, you're going to do like accumulation plus equals error times dt.
It's more of a discrete sum.
Yeah, it's a discrete sum, and the derivative is just like the rate of change, right? So it's that formula, current error times last error over dt, right? Does that make sense? Yeah, that's a good observation. So yeah, and if the error is, so I was up to, if the error is increasing, yeah, the derivative will contribute a positive term, which will attempt to like, I suppose, turn your system around to actually make it approach a target to make that error decrease. Okay, yeah, so quick slide on tuning, and then I'll actually show you me tuning something, I think an elevator. So yeah, when you start tuning, you can make all your constants 0. You want to gradually increase Kp until your output starts to oscillate. And you can like change Kp to like make your algorithm more aggressive or less aggressive. And what you want to do is you want to increase Kd until the oscillations go away. So this is that point about if your drivetrain, for example, is like coming in hot on its target, Kd will slow it down because Kd will account for how fast it's moving. So that's why you can make the Kp oscillate and then fix it with the D term. And then if the controller exhibits, if there's like built up error, you can use Ki to fix that. So if you see like this graph on the bottom, or both these graphs are also like set point. You're comparing the set point to what the system's actually at versus time. So you can see here, there's like your system is at, I suppose, like slightly above 1. Well, it needs to be at 1. So you have this like small gap. And this is error over here, the difference between these two lines. So if you added this up, you would get something that you would like build up this big term that might drive it back down to 1. Okay, yeah. So before I do the demo, I just want to clear up the I term. My best suggestion is to avoid it. Right, the I term is usually counteracting some force. So this could be friction or gravity that causes accumulated error. Right, so instead of having an I term, you can have feed forward. Right, because feed forward can like account for those forces. And the example of the elevator, if you're using an I term for an elevator, that's probably a red flag because you can simply find the voltage. Right? Maybe it's not that simple, but you can use sysid to find the voltage that cancels out gravity on the elevator, and can always add that term to the like elevator input. right? So in this example, it's adding 1 volt to counteract gravity, right? Instead of trying to use some I term. Another example would just be like the entire KSKV equation, right? You calculating 6 volts to prevent the flywheel from slowing down, because if you're using PID on a flywheel, as you approach 3000 RPM, right, your error gets smaller. What's going to happen is friction is going to slow your flywheel down, and feed forward can fix that by just constantly, it'll just calculate 6 volts, and that'll just be maintained to prevent it from slowing down. So yeah. Also, Eric. Oh yeah.
Oh no, not to interrupt, I just want to ask more for PID tuning. I know that the slides mentioned like gradually increasing KP. So basically manually tuning the P, I, well not I, but the P and D values. Is that the only way you can do it, or is there like some sort of equation that can link them all together?
Yes. It's not on the slides, but there is an equation. Sorry, not an equation. A routine that can automatically calculate these KP, KI, KD values, or even like just P or just PD if you only want P or P and D. So the routine is like you're gonna run the system at like, it's called like a bang bang loop, where you run it at like 1 until it like zooms past the target, and then -1 or like 100%, -100%. So it's gonna oscillate around the target. So then this routine will like observe the response. It'll observe the amplitude of the response, plug those into like a table or like a formula, and get back Kp, Ki, and Kd. So this is not on the slides, but 694 has like our open source like code library, and we've implemented that, and you can find it there. And like it has worked for us, so it is something worth doing, something worth looking into. But when you do sysid, like it tells you P, I, or P and D as well. So if you are using sysid, you kind of don't need to auto tune. So yeah, does that clear it up? So yeah, I'm going to show the demo. So yeah, usually don't need Ki, make that 0. So in this PID demo, nice backgrounds. So yeah, this should be PID tuning in elevator. Okay, yeah. So we have a very similar setup here. I have this table of values. I have the height, the target height I want my like fake elevator to go to. I have the voltage that's being calculated from PID. I have P, I, and D in reverse order because it's alphabetical. But yeah. So I just start by setting this to like 10 and then back down to like 3 or 5. So you can see the graph. And if I just start off by making KP like, it's like 0, obviously not doing anything. Zeros for everything is always the first step. Make it 1 though, right? I get this incredibly slow response. So then you can like bump it up from here, and like it doesn't even reach the like target because there's some gravity acting. And I could use Ki here. It might be weird if I do that. Hold on, let me see what happens. Yeah, it jumps off. That's probably really big. Damn. Okay, make that back down to 0. Okay, yeah, it returns to what it was. It's a very slow response. So yeah, if you were tuning this on like a real mechanism that you didn't want to break, you would gradually increase this. But to show what happens, I'm going to put this like to 3. Alright, and I'll make this 0. And then I'm going to just like make it a really high number so it purposely oscillates like a lot. So I think like 100. What would that look like? That wasn't that bad. That feels like not physically possible for an elevator to do though. Okay, yeah. So here I think I've reached an yeah. So I don't know if you want your elevator to do this.
What elevator?
Yeah, he's gone now. I put this back down to 0. Okay. So yeah, if we go back to 1, right, and then if I did it like 5, gets closer, but when I change it again, right, it can probably be made faster. Like put it to 3. All right, let's see if I can get it more aggressive. Let's see if I can get like that small oscillation, and then add on KD. Let go to 10. Put it back to like 7. Yeah, I still need it higher because I want it to like jump over the set point a little bit and then use KD to bring it back down. So that was pretty good. I'm gonna cheat and do what I tuned before. Okay, yeah, so I'm gonna work with this, right? It has a small oscillation, right? So it's coming in pretty fast, and we can just use KD. What if I do a little bit more? We can use KD to slow it back down. So I do 100, and then I change the set point. Okay, nice. So yeah, the extreme does not work. So do 0.1. Let's see if we can get rid of that small jump that happens. I think it was made slightly smaller. I can compare it. So we have that one. Yeah. So from here, wait, can I pause this? Oh yeah. So from here to here, it was the same p-value, but that little oscillation jump was made smaller because my KD term was subtracting off because it was coming in really fast. So yeah, if I keep going with this, keep increasing KI because we still don't want, even this little oscillation, we probably don't want that. Wait, if I run it, increase KI. So it was 0.1, so maybe 0.5. Go down to 1. Yeah, that looks pretty good. Yeah, that was pretty good. Yeah, so it does not jump at all. So 30 and 0.5 works pretty well. I think I had 25 and 1 also worked, maybe. Yeah, so this response was slower. Also worked though. You can tune this to your needs. Generally, the first answer that you get on, the first set of values that works, is probably good enough for the purposes. You don't need to hyper tune it or spend too long doing that, unless you see problems with it. Yeah. So feed forward with PID though, right? This is the culmination of everything we've learned because you can apply feed forward and PID to every mechanism in FRC. So just to review, feed forward takes in 2 set points, calculates a voltage. PID takes in a set point, which can be position or velocity, and a measurement, and then calculates the voltage, right? So the differences between them, PID is reactive to error, so it can handle unexpected unexpected disturbances and efficiencies that feed forward will not. PID, though, it must respond to an error. If there's no, it must respond to a difference between the set point and the measurement. So once PID starts working, it's already behind, which is disadvantage when we know that feed forward can calculate a voltage with that very simple equation. It can do that instantaneously. So clearly they kind of cover each other's weaknesses, complements of each other. But how can we combine them together? So yeah, in the case of velocity control, it's actually pretty nice. Feed forward will do most of the heavy lifting for the velocity controller because we already saw, a feed forward alone is sufficient. But then if you want to add PID onto a velocity controller, what you can do is you can pass in the same velocity set point that you're using in feed forward. Both of them will use the same velocity set point, except PID will also use a velocity measurement, and then the voltage calculated by the feed forward can be added to the voltage calculated by PID and then fed into the system, and they can work. The feed forward and the PID can work together on the same system. Right, so you have PID, which account for small disturbances, feed forward, which is know or uses a model to know like what voltage this flywheel needs to run at. Okay. So then, wait, after 5 minutes, how much time is left? 30?
1 hour.
1 hour?
Yeah, you end at 4:30. It's 3:30.
How do I end at 4:30?
Isn't it only say
I end at 4.
No way.
Yeah, I think it's a cap now.
You're capping. Okay.
Oh my bad. You end at 4 or 5. Keep going.
Okay, so PID with feed forward for position control, right? The same idea of just adding together the outputs of two controllers, right? PID and feed forward, that can work for position as well. But then how do you get positional set points into feed forward, right? What you can do is you can actually track the rate of change between positional set points, right? You can calculate this using, like, I suppose, a slope formula, right? Velocity set point is set point minus last set point over dt, where dt is usually 0.02 seconds, because that's how fast your robot project is running, right? So this technically works, but you'll notice when you change your set point, when I was changing the set point in the simulation, it would just like immediately step up to a value. It was kind of an instantaneous change. So how does like this react to an instantaneous change where you have a very big number in the numerator and a very small one in the denominator? So this number is going to blow up if you don't handle that appropriately. And this graph shows that. The set point rate, the issue is, if you just use this, the set point rate of change would be uncapped. We have this graph here on the left. Yeah, on the left, you have set point versus time. So you have the set point in just units, right? Because this is position control. And it's for the first 2 seconds, it's 0, and then it jumps to 5, right? And it instantaneously changes. And because it instantaneously changes, or technically like in over 0.02 seconds, it changes from one loop of the robot code to the next. If we graph the rate of change of that set point with respect to time, so we have set point rate of change in units divided by seconds, we get this giant spike, right? So if we're using this rate of change and passing that into feed forward as the velocity set point, it would not be a smart idea to pass that monstrosity into feed forward. Like, it blows up to 250 units per second, which is like definitely not physically achievable by the robot, and will also just make the voltage from feed forward really, really high. And then after it spikes, it just goes back to 0, which means the feed forward is not used, right? So having this setup for like position, PID, and feed forward is really not all that useful. But you can definitely make it useful with a little bit of planning. So what you would want to do is limit the rate of change in the set point, right? It's not physically possible for your system to go from 0 units to 5 units like instantaneously anyway. And because it's not physically possible, you can just limit how fast you can change the set point, right? And what you'll end up with is a smoother velocity curve. And because your velocity curve is much smoother, you'll also end up with a sensible acceleration curve. And then you can use the rate of changes in feed forward. And the values that we can limit by are actually pretty nice. They're the maximum velocity and acceleration, right? This is like, it might seem weird to limit how fast you can change your set point. Are you slowing down your system? Are you leaving like speed and response time on the table? And you're really not, because if the system, if it's instructed to go faster than its like maximum constraints anyway, it just won't be able to keep up, right? And it'll have a less consistent response. It's also safer to try and not like instantly accelerate faster than possible, or like try to go faster than maximum speed. Right, you'll just get a more reasonable response. So yeah, what does it actually look like though? The change in position. So the change in position, this is the top graph over here, right? It's no longer just a step, right? It's smoothed out over time, right? It looks like an S, technically. But yeah, it's no longer step. You have a smoothed out change in position. It's constrained by your maximum velocity acceleration. And the velocity curve also looks a lot better. It's no longer like a giant spike. It's a trapezoid, because you have it, you have your velocity increasing, you reach your maximum velocity, and then you'll decelerate. And the acceleration is it's also not a giant spike. I didn't show the giant spike before. It would have been like 2 spikes. But anyway, this graph kind of also makes sense because you have your max acceleration over here. Once you reach your max velocity, you no longer need to change your velocity, and because you're not changing your velocity, your acceleration is 0. And then once you decelerate, it's negative, the maximum velocity. So once you have graphs that look like this, you can safely, if you're trying to combine position PID with feed forward, you can feed this position set point into PID, but then you can feed velocity set points from this graph and acceleration set points from this graph into feed forward, right? So like two rates of changes are going on here. One for the velocity to get a value on this curve, and then another one to get a value on this curve. But yeah. This process is actually called motion profiling, right? It's probably been used in other contexts for path planning, or like this use case. It's probably been synonymous, but this is what motion profiling is, or this is how we think about it. Helping.
Time is up. Break time.
Break time?
Yeah.
Okay, I still have 30 more minutes, so.
Yeah, after this.
Okay. Just stand here.
It was already over.
I was, but then I got really nervous. No, it was definitely over. Yeah, I should give me that.
No, it was actually, I really like this stuff. And then this thing won, so
Aiden's show was just more interesting. Yeah, I can imagine.
The timing's hard. I accidentally ended my talk 10 minutes early because I thought it was 50 minutes instead of an hour.
Yeah.
You said like, so you like plug your voltage values back into your PID, combining PID and forward.
You just add them together.
Yeah, so I had a question, right? So PID, like both the set point and the measurement have to be the same exact units, right? So just the measurement that like PID takes in would not be like a speed or something.
Yeah, for position it would be position and position, and then the feed forward.
No, yeah, but like since it's taking in the output of like the feed forward, it has to be voltage.
It's not taking in the output.
It's not.
You're just adding them together.
I don't understand it. But it's like, you mean like, it's also, wait, so it's like, the feed forward just takes in like the speed of the thing, right? And then like calculates some voltage.
Yeah.
And then PID also takes in that speed, also takes in some that value.
Yeah.
And then you combine the two together.
Yeah. If for a position though, you're going to calculate. No. You're going to calculate the rate of change of the position set points and feed that into feed forward.
Rate of change of the position set points?
Yeah.
Yeah, that makes sense.
Yeah. I think I have to present. I know what this is gonna look like. I know what a vector field is.
It's like the equation. We have like a right here. Every matrix has to be replaced. There's no resources for everything to use.
Guys, when do I start again? Are you sure? Yeah. Oh, it's just.
Shut up.
No, it's like, why did people leave that? They should have locked the doors.
Oh,
You didn't know because I think Brian, the mentor that was here, he thought that he just got cut off. I'm not sure. It's just like,
changed this one.
What are you talking about? Bro, I didn't know what you're talking about, bro.
Don't be rude. Answer the goddamn question.
I mean, yeah, I get turned on by this stuff.
Miles, it's still.
Oh, that's true. It's still true. At least they know they're getting this information from someone credible. If my teacher doesn't get turned on, the mic's not on. Where the front That's right. Sam, the one of the block size shirts. Yeah, I saw people saying this. It's a rock. Whatever you're saying is wrong. Okay. What were you gonna do? What's your question?
Like PID, right?
The PID values, the PID constant is really small.
Oh.
Yeah, okay, I'm gonna say that. Jen! Get back here. Your brain's open.
Yeah, the brain actually is like moving.
Yeah, it's at one minute start. No, we're at 3:40.
Not even good, it's such a bad
You actually don't have to
And then you let me back.
Cookie, you want one?
What the heck? That's so rude.
Open your mouth.
No. Oh, you're gonna throw it?
Yeah.
Too bad person, bro.
Presentation's over. This is the end.
We'll have to end it with this. Sam, can I start?
Yes, you can start.
I wasn't asking you. No, I'm kidding.
You are not
You guys have the double iPhone charger? You guys have the double iPhone charger?
Not back here, I don't think.
What are you doing? Maybe you're Nokia. I also don't have a charge.
Alright, I'm gonna start at 3:40. I can work with 25 minutes. No, it's 3:40.
Yeah.
Alright, Ben, get up there. It's your presentation.
Okay, your turn.
We are going to code.
I can get you the water. Vincent, sit down. Okay. Alright. Part 2. Samantha, shut up. Okay. Presentation listeners, I'm gonna start up again. So buckle your seatbelts. Where were we? Oh yeah. So motion profiling. It's when you smooth out your positional set points so that you can take the rate of change, and plug the rate of change of your position set point into feed forward. Use the voltage from feed forward, and then you have a PID loop that takes in position and takes in the position measurement, or the position set point and position measurement. Use those voltages, add them together, right? That's kind of what we're doing here, right? We've figured out PID with feed forward for position as well. It requires a motion profile over your position set points so that there's a well-defined velocity and acceleration between set points. One note is that when you combine feed forward and PID, you ideally want your feed forward to do most of the work. So if your feed forward is doing most of the work, then it's like the KV, KSK constants are just going to be what they are. But then if feed forward is doing a lot of the heavy lifting, the PID constants can be smaller, so they can be less significant because they don't have to like account for as much movement. So if you tune it with like SysID, that's what you'll notice. So yeah, what's left? Oh yeah, one note. Now that we know about motion profiling and like how, if you smooth out your set point, you can take the rate of change and get something you can like use in like feed forward. We can do the same thing with velocity, right? Feed forward takes in both velocity and acceleration. So when we have a velocity controller, we can take the velocity set point, plug that into feed forward. But what if we do want to account for acceleration, right? And pass that into feed forward as well to kind of get a more accurate response. What we can do is just apply not a motion profile but a rate limit. So a rate limit will just be saying like how fast can it change in like one what's the maximum like the maximum acceleration, because you're doing velocity, so you need to cap out the acceleration. What this will cause a smoothed out velocity. So when you take the rate of change to calculate acceleration, the acceleration set point at the bottom, right, you'll get back something you can pass into feed forward. So yeah, that's just everything's complete now. Apply this knowledge to any mechanism. SysID, another note about SysID, just coming back to like tie everything together. SysID knows that PID is going to be like combined with feed forward. So on top of KS, KV, KA, and potentially KG if you're using an elevator, SysID is going to calculate optimal KP and sometimes KD gains, and it'll allow you to select whether or not you want a position controller or velocity controller. So it'll tell you feed forward and PID. So if you're using SysID, you don't really have to tune anything. It's actually really nice. So notes I had for practicality. When you're doing set voltage, in general, we're pretty sure it's good practice to make sure that voltage compensation is enabled for your motor controllers, right? So for like a CAN-SPARC Max, there's like an enable voltage compensation method. And this is really important if you're using these algorithms, not on the robot code, but using the fact that they're implemented on the motor controller, right? You definitely want to enable voltage compensation. So yeah, another thing is like, it's not always convenient or possible to characterize. So SysID, system identification, I guess the verb for it is characterize. It's not always convenient to characterize a mechanism, so sometimes it's fine to just stick with PID. So yeah, control theory and code. So we have we have 20 minutes. So I can go over the way that 694 codes, like what I've discussed. So we have a team library called StuyLib, right? Named after our school's library. And we've implemented our own control theory library based on like the understanding of control theory we have in our slideshow, right? So the way we like organize everything in the slideshow, that's how we've designed our code library. So we've made sure the big three of PID, feed forward, and motion profile were all able to be easily used in conjunction with one another. That was kind of our design goal with the library. If I have time at the end, I can show what WPILib's control theory library looks like. but it's a little bit harder to use all three algorithms together. There's like more, it'll take up more like lines of code, be harder to maintain, stuff like that. The only other part of Scilab that it's like this like control theory stuff relies on is filters. So let's just give a quick explanation. Hopefully like just like the naming makes sense. So it's just a filter. A filter accepts a value and returns a new filtered value. So rate limits and motion profiles are implemented as filters, right? So like they take in the set point that you want to go to, and when you create a motion profile or a rate limit, you're giving it that like maximum constraint. So it'll return the new filtered value it's returning is one that abides by the maximum constraints. And yeah, the fact that they're both filters is important for like the, I guess, polymorphism in our code, just to make it more flexible. So yeah, the control theory library starts at the controller.java file. It's a controller class. It's an abstraction for any control algorithm, and it will need the following methods. So here we see several important methods. There's update, which we see takes in the set point and takes in the measurement. If you can see my cursor at the bottom, that will return the voltage that you can feed to a motor. And yeah, it'll like update the state of the controller. There's also these getters, right? Get set point, get output, which is just like the voltage is calculating, getting a measurement, and getting the error, which will just do get set point minus get measurement, right? There's also a method is done, which will tell you if like your controller is within an acceptable error. And then there's these three methods over here. Oh my god. So these three methods is where you implement like a rate limit and a motion profile, right? Yo. I hope she never finds a security desk. Okay. Anyway, so yeah, so we have the ability to apply filters to like the measurement, the output, and the set point. So that would be like when you pass in set point and measurement to the update function, it'll pass them through the filters you specify first, and then before it gives you back the output, if you have an output filter, it'll calculate, or it'll pass that through the filter, right? So this is this set point filter is kind of hinting at where you want to implement rate limits and motion profiles, because like you just apply a filter to the set point and it'll like smooth everything out. PID controller. It's a standard PID controller. You can find literally the same class, not the same class, but a very similar one under the same name, WPIlib. Ours is just like in our library, so you can like use it interchangeably with the classes we have. And this has like it has the update method because it extends from controller, so it'll like inherit that method, and then you just are able to set the P, I, and D values. You can set an integrator filter. I think there's a note in the slideshow that like the I term, if you are using it, it requires some housekeeping. So in that case, like you'd use an I filter, or you just like specify the range and the limit. But I generally set it to 0. But yeah. Then there's a feed forward. Oh shoot. Then there's a feed forward. I presented 2 equations before, one with kg and one without. So you just want to choose which one you want to use. So that's feedforward.elevator and feedforward.motor. So these are the names of classes. So you would do new feedforward.elevator, pass in the 4 values, or do new feedforward.motor and pass in the 3 values. And once you do this, you want to convert it into a controller. So you would do dot position if it's for a position controller, and dot velocity if it's for a velocity controller. So like I was talking about the differences between the two. For a velocity controller, it only takes the rate of change once to get an acceleration set point. For position, it'll take that like discrete rate of change twice to get velocity and acceleration. But yeah, so in code, like once I use these in code, you might find stuff that looks like this inside a subsystem, right? Okay, this is actually talking about a method. So one of the methods in the controller class is an add method, and it takes in other controllers. And because PID and feedforward are also implemented as controllers, you can like compose them together. So when I do dot add, I have the PID controller at the top. I have the feed forward on the next line, and I just have like velocity or position here, right? And then but I combine them with a dot add. So then the next time I call dot update, it'll loop through PID and the feed forward, and it'll like add the voltages they calculate together, right? So this is super convenient for keeping your control theory code clean inside a subsystem. So instead of having like several fields of your class just dedicated to control theory or your control algorithm, you only have one because you've composed them together like this. And this is what I mentioned before. You can also add a set point filter on top of like what you have already. So for the feed forward that's dedicated to velocity, right? Because I call dot velocity here, I do set point filter new rate limit. For the position controller, which I know because I'm using dot position for the feed forward. Also, like if I was just coding this myself, like I'd have to make a documentation that this is like a position controller. That would be a good idea. But then dot set point filter, and I use a motion profile, which will take in the maximum velocity and a maximum acceleration here, where this is just maximum acceleration because you already have a velocity set point. So then, okay, yeah. So then one thing I didn't show, but I should have, is dot update, because no matter like how many methods you call on this stuff, right? If you call dot add or dot set point filter, it's still a controller, right? And because it's still a controller, you can still use dot update on it. So I should have shown using dot update. You just pass in the set point and the measurement. But luckily, oh yeah, one more thing. There's angle alternatives for position control. There's like an A PID controller, and if you wanted an angle feed forward, you'd call it that angle, and you can use like, there's filters A rate limit and A motion profile. But this is stylib stuff. This is a big difference between stylib and WPIlib. WPIlib handles angle differently. You usually want to do like dot set continuous input and do like negative pi to pi radians, I think, something like that. Depends on your units. But yeah, all these classes do the same thing, except they just use angle math, and then like it'll do what I mentioned at the very beginning, where it like will take the shortest route because it's on a circle. So then I left time to code at least one of these with like this control theory knowledge and approach a subsystem using control theory. So I left time for one of that. But before, I want to field any questions about motion profiling and combining feed forward and PID, or stylib's like approach to control theory code. Is there any questions about those? Yeah.
What's the process of running sysid? Like, do you actually run it? Do you simulate it, or do you run it on your real mechanism?
Oh yeah, you should definitely run it on your real mechanism. So these like coefficients will kind of account for the like dynamics of your system as well as inefficiencies. So it's good to run it on the real thing. And then I was showing before, I can open sysid again. There's a couple parts to it, and there's also like the FRC documentation online. Will probably say what I'm about to say, but like written down. sysid is going to run like that voltage versus velocity acceleration test on your robot. So you need to specify like what motors and encoders like you want this test to use. So that's this section, the generator. And then you hit deploy, and it like makes robot code that it deploys to your robot. And then you're going to connect over here in the logger. So like up top here, I'll type in like 694, and then I'll connect to the network table of the robot so it can actually send over data. And I'd again type in 694, and it can use our team number to like get the IP and connect. I'll apply in whatever, and then I'll select what type of project I'm working with. So here you see elevator, arm, simple. If you have like some sort of miscellaneous thing, like a motorized intake we have. If we were to like do that, we'd do simple probably. And then just like a unit conversion. The gearing's over here, so the gearing is like motor turns to like output rotations, and then you do here, you select what unit, and you do like how many rotations to get this unit over here. So for meters, This would be like your wheel circumference or whatever. In meters, of course, because you selected that. And then the 4 tests it's going to run to actually collect this data is a quasi-static test, forward and backwards, and that would be like consistently ramping the voltage at a set rate so that you can kind of observe the velocity, observe that kV value, I'm pretty sure. And then the other test is going to be a step voltage, which will just like instantly instruct everything to go to a voltage, and that'll induce like a big acceleration, and it can observe Ka. Yeah, so you run these 4 tests, right? You like click the button, and it'll be like, okay, you should enable autonomous now, and it's gonna tell you like, oh, we won't stop it for you. So you have to like actually watch where your robot's gonna go, because if you have a drivetrain, it'll like run forever. Once you run those 4 tests, you'll get a JSON file with a bunch of data. You'll go over to the analyzer over here. You'll open it. Sam, do you have any robot projects on here?
Yeah, Counter-Strike Global Offensive. Yeah, that's my favorite project.
Yeah.
Autodesk Robotics.
Oh, this is cool. Dorcas, nice. Okay. So yeah, I'm gonna open a sysid. I hope it's in here.
That is probably not updated, so like I'm
Dude. From February 9th, I was like the day. Simple shooter, Styrami. Oh man. Do I have time to pull? True.
How old is that one?
This one's really old, but we like had to sysid it. Anyway, it might come around to like getting a JSON file, but basically you'd select it. It would just ask you where to find it from, and then it would open it, and there'd be like 3 rows: KS, KV, KA, for your feed forward, and then this feedback analysis section would be PID gains, and you'd select if you're controlling velocity or position for this PID. And then in code, you could use those numbers in a feed forward PID sort of ordeal. So yeah, that's our sysid process. And then we ideally save the JSON file to our like robot projects, but I don't think they're on this computer. But yeah.
Is that something you just run once, like before regionals? Do you run it like throughout regionals to tune things? Or?
We run it once when the robot works. Like once it's driving around, like we'll generally want to run this because then we can start testing autons.
Yeah.
But yeah.
Could you explain which like mechanism we should use for shooters?
For shooters, oh yeah, that's a good point. I think for shooters it's probably simple, and then you want to make it rotations. Oh yeah, this is actually pretty rough. See, because I think it's just because of what we were doing last season that we preferred rotations per minute for the shooter. But when you select rotations over here, it kind of locks you into one. Like you can't change that number, so you're kind of stuck at rotations per second. So we kind of did a hack where we went into the JSON file and changed the units for rotation to 60 to ensure that we would get rotations per minute, and then we like got the right KS, KV, KA values.
Just change it to meters, and then we get 60.
Oh, okay, yeah, that's a good point. You can also do it like this. This is a little weird, because like your wheel's not going any meters, but yeah, that works too. We got it in rotations per minute. But yeah, that's our sysid process. So are there any other questions? Oh, yeah.
Never used it, but I've seen like instead of PID controllers, PIDF controllers.
Mm-hmm.
That just try to contain all of the constants into one.
Yeah, that is. Yeah, PIDF controller is like a little old. It's the F is of course feed forward, but there's only one number for feed forward, which is not as accurate as having KS, KV, and KA. So KF would be analogous to KV, but then once you add on those 2 other terms, you get like a better response. Does that make sense? Okay, yeah.
So I have a question more like specific implementation. Should I like ask you like later, I guess, because it might take a while?
Yeah, you can ask later.
Okay.
Oh yeah. One thing is, I have my email over here, miles.pazetsky@stuypulse.com, and it can Zoom, or you can ask me about control theory, or you can ask me for my Discord, so we can communicate, not over email, because that's dumb. Discord.
So my God. that the end?
No, it's not the end.
Oh. My bad.
Okay. So yeah. So there was another question. Yes.
Have you ever ran into issues with this ID just like not working?
Yes. On an old robot though. So because it wasn't our competition robot, we just gave up and moved on. So we never got to the bottom of why that was happening. And since then we've never run into it. Sam, do you remember Edwin where we tried characterizing the shooter?
Dude, I know the shooter just it kept breaking.
Yes. It kept breaking.
Like the drivetrain.
Yeah. So the shooter on this robot didn't work, but the drivetrain was characterizable. So yeah.
I think it was like a wire in the shooter or something.
Yeah. Okay. Any more questions? I can speed run this code. So yeah, I suppose I'll speed run code. An example implementation of, let's say, the elevator, because I think I was talking about shooters a lot. Pretty simple. So you can do an elevator. So if you were in attendance for the subsystem design presentation, you know that we would usually make a simulation or like an interface or whatever, but for the sake of this presentation, I'm not going to do that because I'm not going to run this code. So I'm just going to start with like, I know on our 2018 robot, our elevator had 4 motors, right? So I'm going to make I'm gonna blame. Oh, that was motor controller. Okay, so I've made this fake class motor controller. Since you like motors. So let's say there's 4. I probably should have just ignored this step. So yeah, we just make our 4 motors. Right now we want a control algorithm, and we know for a elevator, we want the target height, right? Or we want to be controlling the height. That's the state of any elevator. So just right off the bat, I'm going to do a private target height here, and I'm going to set that to 0 right at the start. And then to actually make the measurement of the height approach the target, we're going to, of course, need a control algorithm. So I'm using stylib in this case. So I'm going to add my field to this class as a controller base class. Right, controller. And then I'm going to initialize it. So then based on like what we learned, if I characterize an elevator, I'll get feed forward KS, KV, KA, and I'll get KP and KD from the feedback analysis. So I'm going to use like PID and feed forward and a motion profile because it's position. So we want to like smooth out the position so it abides by maximum velocity and acceleration. So I'm going to do that now. New PID. So I don't know the numbers. So 6, 9, 4, and then dot add new feed forward. So then I have the feed forward dot elevator, which the only difference between elevator and motor feed forward is like kg. So if I import this, I have to make more numbers. 1, 2, 3, 4. So okay. Oh yeah. So then this class feed4.elevator is just like a model, right? And then we need to actually make it into a controller that will like take the rate of changes for us. So that would be doing dot position, right? So this will take in a position set point and take the rate of change twice. But to like safely take the rate of change twice, I need to do a set point filter on it. So this would be my new motion profile. And we need more numbers. 1.5. Right, so this is my complete, for my elevator subsystem, these two fields and these two these two fields, this like 3-line initialization is all I need to implement motion profiling, feed forward, and PID, right? So then I'm going to add the periodic. One thing I've ignored so far is a measurement, so I'm quickly going to make a method that will average out the position of all 4 motors. So yeah, in this fake motor controller class I've created, I have access to the speed, the position. So I'm just gonna return total divided by motors.length. Okay. So you don't, when you have like a group of motors, you don't want to feed them separate voltages, right? You don't want, if they're working together, you don't want 4 different controllers, because if they're all for the same gearbox and like one is slightly below the target, one is slightly above, they'll be going in different directions, right? And that's like really bad for the gears and such engineering. But so this averaging out the position values is a pretty good solution, right? And then we just pass in this position. This also assumes every motor has an encoder, but if it doesn't, if it's only one, you might as well just use the one, as long as you don't have like 4 different things going on. So then the only thing I have to do is the same for loop, which I'm going to copy, and then just like, this will be motor.set voltage, or what I can do, I think I want to controller.update target height, because that's the set point, and then get position. And this will return the voltage that I want to calculate with. It'll return the final output, but I technically don't have to store it because I can just do get output, right, to retrieve it. But if I did like, that would be the same thing. And if I just used output over here, it'd be all good. So yeah, this is my elevator, my motion profiled elevator. And yeah, I can. Do I have time left?
No.
No. Okay, perfect. Perfect. I was gonna show you the WPI lib version, which I'll spoil it. It's just more of a mess. We just thought that's pretty clean. So yeah, in the slide deck, which will be emailed, I have some more references over here, and I showed my slides already, or my email. Do there happen to be any questions? 1 second. All right. Email on the board. Okay, super good.
Super good.